Beneath frozen crusts and perpetual night, hidden oceans stir on distant moons. Once we thought Earth seas were unique, but now Europa, Enceladus, Titan, Ganymede, Callisto, and Triton whisper otherwise. In these dark waters warmed by tidal flexing or ancient heat, astrobiologists glimpse possibility. Could life thrive in such Stygian depths, feeding on chemical energy as it does at Earth's hydrothermal vents? Spacecraft have flown past, some even sampling erupting plumes, and the awe is profound. If life began twice in one solar system, the universe may be far less lonely than we imagined. What follows is an exploration of these ocean worlds, their geology, chemistry, habitability, and the missions that may uncover their secrets. Europa's surface is a cracked tapestry of ice, its reddish fractures and chaotic terrain hinting at a global ocean below. Orbiting Jupiter every 3.5 days, it is stretched and squeezed by gravity, generating heat that prevents its sea from freezing solid. Dark lineae scar the surface, and jumbled chaos terrain suggests a mobile layer underneath. Suspicion of a hidden ocean became near certainty with Galileo's flybys in the 1990s. Its magnetometer recorded subtle distortions, best explained by electric currents in a salty, conductive ocean beneath the crust, a faint magnetic echo of Jupiter's field, the smoking gun for a global sea. The ocean may lie 20 kilometers below, 60 to 150 kilometers deep, with more water than all of Earth's oceans combined, and it may not be entirely sealed. In 2012 and 2016, Hubble spotted faint ultraviolet glows consistent with plumes venting to hundreds of kilometers. If real, these geysers would allow a spacecraft to taste Europa's ocean without drilling. NASA's Europa Clipper, launched in 2024, was designed to do just that. Europa's surface chemistry also hints at what lies beneath. Spectrometers detect salts such as magnesium sulfate, likely residues of upwelled ocean water. There are even tentative detections of organics and oxidants, possibly transported from the depths. If true, Europa's crust is not a barrier but a conveyor, carrying potential building blocks of life from ocean to surface. Europa's case for life rests on three essentials: water, chemistry, and energy. The water is abundant, a global ocean kept liquid by tidal heating. Its chemistry looks promising too, likely salty, electrically conductive, and in contact with a rocky seafloor, where water-rock reactions could enrich it with life-essential elements. Hubble's plume detections even hinted at hydrogen and oxygen, suggesting surface radiolysis may feed oxidants into the ocean. Europa also seems to have energy. Tidal heating that maintains its oceans likely powers hydrothermal vents on the seafloor, much like those at Earth's mid-ocean ridges. On Earth, such vents sustain entire ecosystems through chemosynthesis rather than sunlight, from microbes to tube worms. Even in perpetual dark, chemical gradients, hot fluids mixing with oxidized waters, create disequilibria life can exploit. Methanogenesis, the ancient metabolism combining hydrogen and carbon dioxide, could occur here too if hydrogen seeps from vents and oxidants trickle down from the ice. NASA's Kevin Hand has described Europa as a world with an ocean against a rock-water interface, with the potential for a rich broth of chemicals, a planetary petri dish beneath the ice. Still, Europa hides its secrets well. The surface is lethally irradiated, so any life must dwell far below, perhaps as simple chemoautotrophic microbes. Detecting them may depend on indirect biosignatures, unusual gas ratios in plumes, isotopic anomalies, or organic molecules with biological patterns. Upcoming missions, NASA's Europa Clipper and ESA's JUICE, will map the ice shell, probe its depth with radar, measure magnetic responses, and perhaps catch a plume in the act. These data will clarify Europa's ocean, its thickness, salinity, and energy. If the right conditions are confirmed, water, chemistry, and energy sustained over time, many scientists believe life could have emerged there. And if it has, it would reveal biology as a cosmic inevitability, not an earthly accident. Saturn's moon Enceladus, only 500 kilometers wide, stunned scientists in 2005 when Cassini saw towering plumes erupt from the cracks at its south pole. Once thought an inert ice ball, Enceladus suddenly revealed itself as a prime astrobiological target. Cassini flew through the geysers many times, tasting a cocktail of water vapor, organics, ammonia, CO2, methane, and most importantly, molecular hydrogen. That hydrogen was a breakthrough. It is likely produced by hydrothermal reactions on the seafloor, and could fuel microbial methanogenesis, the same ancient metabolism that may have powered Earth's first organisms. With H2 and CO2 both present, Enceladus's ocean seems primed for life. As NASA's Thomas Zurbuchen remarked, it is the closest we've come so far to identifying a place with some of the ingredients needed for a habitable environment beyond Earth. Enceladus checks nearly every box. Cassini confirmed a global ocean beneath 20 kilometers of ice. It found simple and complex organics, and in 2023, reanalysis revealed hydrogen cyanide, a key precursor to amino acids, along with oxidized organics, suggesting diverse chemical pathways. Tiny silica grains collected in Saturn's E-ring point to hot water circulating through rock, strong evidence for hydrothermal vents and an active heat source in the core. This paints a compelling picture, a small world hosting a miniature version of Earth's deep oceans, complete with warm springs, mineral-rich fluids, and potential microbial niches. Even methane excesses in the plumes have raised eyebrows, possibly biological, though abiotic explanations exist. Only phosphorus and sulfur remain unconfirmed, but they are likely present in the core. On paper, Enceladus has nearly everything life needs. Whether it is actually alive remains the unanswered question. Enceladus's plumes make it uniquely accessible. Instead of drilling through ice, spacecraft can fly through the spray and sample the ocean directly. Cassini did this many times, though without instruments built to detect life. Future missions could change that. The Planetary Science Decadal Survey recommended an Enceladus Orbilander concept, a craft that would orbit, repeatedly sample plume material, then land near the South Pole to analyze fresh deposits for biosignatures, such as amino acid ratios, complex lipids, or even microbial cells. This reflects how far Enceladus has risen, from an obscure moon to a prime contender for hosting life. In 2023, the James Webb Telescope revealed just how active it is, spotting a vast plume stretching 9,600 kilometers, 20 times Enceladus's diameter. Webb mapped how this torrent of water feeds Saturn's E-ring and surrounding space, confirming Enceladus is venting its ocean on a colossal scale. It's a natural sampling system, a well from abyss to space. One can't help but feel an awe at this tiny moon bleeding its ocean into the void, a beacon in Saturn's night, proof that even the smallest worlds may hold answers to the oldest question: are we alone? If Europa and Enceladus are ocean worlds of water, Titan offers something stranger: seas of methane and ethane. Its surface, at minus 179 degrees Celsius, is cloaked in orange haze, with rivers, rain, dunes, and lakes sculpted from exotic materials. Water ice is rock hard, methane falls as rain, and tholins, tar-like organics, coat the ground. Stand on the shore of Ligeia Mare, and you'd see a glassy hydrocarbon sea under a dim orange sky, Saturn perhaps glimmering at twilight. Such alien seas invite speculation. In 2015, researchers proposed azotosomes, methane-based cell membranes built from acrylonitrile, abundant on Titan. In simulations, these membranes could be flexible and stable in liquid methane, suggesting life might exist with methane as its solvent. Cassini added intrigue. It found less acetylene and hydrogen at Titan's surface than expected. A pattern astrobiologist Chris McKay had predicted if microbes were consuming them. Some saw hints of metabolism. Others cautioned that exotic surface chemistry could explain it instead. No proof yet, but Titan remains the only place where methane life is considered a serious possibility. Titan may also hide a second, more Earth-like habitat, as subsurface water ocean perhaps mixed with ammonia to stay liquid. That makes it doubly compelling. Two potential abodes for life, one water-based and one methane-based. Meanwhile, Titan's atmosphere is a vast chemistry lab. UV radiation and charged particles break apart nitrogen and methane, building a zoo of organics that rain or snow down. Cassini detected molecules from ethane and hydrogen cyanide to complex precursors of amino acids. In 2023, JWST filled a missing link by detecting the short-lived methyl radical, clarifying how Titan's haze is forged. This smoggy world may resemble a frozen version of prebiotic Earth, offering clues to how chemistry edges towards biology. If life exists on Titan's surface, it would be like nothing we know: slow, cold, and methane breathing. Perhaps tiny organisms lurk in the mud by lake shores, or spore-like forms await the seasonal methane rains. Even if sterile, Titan is still invaluable, a natural experiment in planetary-scale organic chemistry. Titan first revealed its surface in 2005, when ESA's Huygens probe parachuted down, capturing hills carved by rivers and landing on a plain of rounded ice pebbles coated in organics. It even measured a damp spot beneath, hinting at a moist methane-rich ground. The glimpse showed Titan to be geologically familiar, but chemically alien, a landscape sculpted by liquid, yet made of ice and hydrocarbons. Now NASA prepares to return with Dragonfly, a nuclear-powered rotorcraft the size of a car, launching in 2027 and arriving in 2034. In Titan's thick air and low gravity, flight will be easy. Dragonfly will hop across the surface, analysing composition, searching for complex organics, and probing how far prebiotic chemistry has progressed. Its prime target, Selk Crater, may have once mixed water and organics in a natural chemical reactor. Over a planned 3-year mission, Dragonfly will study dunes, crater rims, and perhaps even a methane oasis, assessing Titan's habitability both for exotic methane life and more Earth-like chemistry. Titan also pushes us to rethink habitability itself. If life can exist in liquid methane at minus 179 degrees Celsius, biology may be far broader than our imagination. If not, the silence will be just as meaningful, Perhaps water holds a unique role that even Titan's bounty of organics cannot replace. Either way, Dragonfly's journey invites reflection. Titan's haze may hide answers to questions we don't yet know to ask. Jupiter's largest moons, Ganymede and Callisto, are quieter than Europa, but may also hide vast oceans beneath their ice. Ganymede, bigger than Mercury, is the only moon with its own magnetic field. In 2015, Hubble observed its auroras shifting in a way best explained by a conductive saltwater ocean, about 100 kilometers down. Models suggest this ocean lies sandwiched between ice layers, a club sandwich structure that may limit contact with rock and thus nutrients. Still, it could contain more water than all of Earth's seas. Callisto, heavily cratered and geologically ancient, shows a similar magnetic signature. Initially, its ionosphere muddied the picture, but a 2025 reanalysis of Galileo data strongly suggests a deep, briny ocean beneath 100 to 150 kilometers of ice. Its persistence may be due to ammonia antifreeze or residual radioactive heat. If confirmed, 3 of Jupiter's 4 giant moons, all but volcanic Io, would host subsurface oceans. Habitability here is less certain. Both oceans may be cold, isolated, and nutrient-poor, compared to Europa or Enceladus. Yet even intermittent contact with rock or dissolved volatiles from formation could allow niches of chemistry. Upcoming missions will test this. ESA's JUICE, arriving in 2031, will orbit Ganymede and probe its ocean with radar and magnetometers, while NASA's Europa Clipper will make complementary flybys. Together they may finally confirm these hidden seas. Philosophically, Ganymede and Callisto embody the idea of abundance without vitality. If their oceans prove sterile, while Europa or Enceladus teem with activity, it would highlight the need for constant energy flux in sustaining life. In the far future, cryobots or fleets of robotic swimmers could one day descend through their ice, illuminating the black waters below, perhaps catching the glint of something alive, or only the silence of barren seas. Far out at Neptune orbits Triton, a strange moon captured from the Kuiper Belt. Its retrograde orbit hints at a violent past, when tidal heating may have melted its interior. Voyager 2's 1989 flyby revealed an active world, smooth young plains, bizarre cantaloupe terrain, and geysers of nitrogen dust rising 8 kilometers high. In the frozen outer solar system, Triton was alive. Evidence suggests it still hides an ocean. Its resurfaced plains imply internal warmth. Its crust is water ice topped with nitrogen and methane, and models show that with ammonia or salts, liquid could persist 100 kilometers below the surface at minus 80 degrees Celsius. Triton may be Pluto's cousin, both icy dwarf planets with likely subsurface seas. The astrobiological potential is speculative but intriguing. If its ocean touches rock, water-rock chemistry could provide energy. Its surface shows organics, possibly cycling into the interior via cryovolcanism. Nitrogen ice and trace methane also produce complex organics under sunlight. All ingredients are present. The unknown is how much energy remains. The plumes Voyager saw could be shallow solar-driven eruptions, or they may hint at deeper heat. Detecting an induced magnetic field in future missions would confirm the ocean's existence. Triton has not been visited since Voyager, but NASA considered a Trident flyby to study its plumes and geology. Though not selected, Future missions in the 2030s and 40s may return with orbiters or landers, capturing plume chemistry and probing the moon's hidden sea. Triton stretches our view of habitability. Far from the sun, it still has weather, seasons, volcanism, and possibly an ocean. It shows that the habitable zone is not just a band around stars, but can exist deep in icy shells, powered by physics rather than sunlight. If confirmed, Triton could mark the solar system's farthest ocean refuge, a last flicker of warmth at the edge of the dark. Ocean worlds force us to rethink habitability. They show that life may flourish without sunlight, powered instead by geology, tidal heating or radioactive decay driving chemical reactions. On Earth, entire ecosystems thrive around hydrothermal vents, proof that chemosynthesis can replace photosynthesis. By analogy, Europan or Enceladian life could begin with microbes oxidizing hydrogen or methane, perhaps even evolving into simple multicellular forms grazing in the abyss. Detecting such life would rely on biosignatures, unusual gas ratios, for example excess methane with hydrogen scarcity, complex organics unlikely to form abiotically, or molecular imbalances like chirality. On Enceladus, plume chemistry already hints at methanogenesis. On Europa, measuring oxidants versus reductants could reveal whether biology is breathing the ocean. Ultimately, in situ sampling, a plume fly-through, or a cryobot probe, may be needed for certainty. The basic recipe for habitability, water, chemistry, and energy, appears in many places. Enceladus and Europa are strong candidates. Titan tests the limit of methane-based life, and Ganymede or Callisto might host colder, quieter seas. If Titan is sterile, it may show that water is uniquely suited to biology. But even if methane-based microbes exist, then life could be staggeringly common in the universe. Exoplanet discoveries only reinforce this. Moons and planets with subsurface oceans may be widespread, far beyond the habitable zone. Enceladus, orbiting in sunlight only 1% as strong as Earth's, still has warm water. Life may find a niche wherever physics sustains liquid oceans. A second genesis in our solar system would be transformative. It would shift life from miracle to inevitability, extending the Copernican principle to biology. Earth would be just one of many living worlds. Panspermia remains a possibility. Meteorites could have spread microbes between moons. But if alien life proves wholly distinct, it would confirm life sparks independently wherever conditions allow. And if we find nothing, that too would be profound. It would suggest that water, energy and chemistry are insufficient, that life is far rarer than we hope. The universe might be filled with habitable, yet barren oceans, countless sterile worlds awaiting a genesis that never comes. A melancholic thought, but one that deepens the miracle of life on Earth. The next 2 decades will transform our knowledge of ocean worlds. NASA's Europa Clipper will make dozens of close flybys, mapping ice structure, scouting for plumes, and measuring magnetic and gravity fields to pin down the ocean's depth and salinity. ESA's JUICE will orbit Ganymede, probing its ocean and magnetic field while also studying Callisto. Together they'll reveal in detail the architecture of Jupiter's hidden seas. At Saturn, concepts for an Enceladus orbolander envision precision plume sampling, fresh ice collection, and even the search for direct biosignatures. If funded, it could launch in the 2030s. NASA's Dragonfly rotorcraft arriving at Titan in the 2030s will hop across dunes and crater floors, analysing organics and probing prebiotic chemistry. Meanwhile, engineers are designing cryobots that could melt through kilometers of ice and release swarms of robotic swimmers, a vision edging from science fiction toward reality. Philosophically, the stakes are immense. If we find life on even one other world, it implies the universe is filled with biology. If not, it underscores Earth's singularity and deepens the silence of the Fermi paradox. Either way, the quest reshapes our place in the cosmos. Picture standing on Europa's frozen plain under Jupiter's looming bulk, or drifting in Enceladus's abyss as hydrothermal vents glow in the dark. Such visions are no longer fantasy, but plausible futures. From Galileo's discovery of the moons in 1610 to today's understanding that they harbour oceans, we've reached a turning point. Our generation is the first to grasp that the solar system has not one ocean, but many. Life, if it exists elsewhere, is likely waiting in the dark, beneath ice shells and in methane lakes, unseen but alive. As we send probes to pierce the ice and sample alien seas, we carry a quiet hope that somewhere in those brines, microbes are turning geochemistry into biology. Should we find them even in the humblest form, the cosmic loneliness will be forever diminished. Until then, the ocean worlds beckon, with their plumes, their mysteries, their silent seas. They are scientific frontiers and spiritual mirrors, reminding us that life may emerge in the most shadowed corners of the universe. The stage is set, the dark oceans await. Whether life plays upon that stage is the revelation we seek, one that could echo across time and space, changing us forever. From Europa's tidal seas to Enceladus's geysers, Titan's methane lakes, Ganymede and Callisto's hidden depths, and Triton's distant ocean, these moons expand our idea of what it means to be habitable. They show that life might arise in darkness, sustained by heat and chemistry, rather than starlight. Upcoming missions will probe these seas with unprecedented precision, perhaps detecting life's signature in a plume or an icy plain. If we succeed, it will reveal that biology sparks not once but often, implying a galaxy alive with possibilities. If not, the silence will underscore Earth's fragility and deepen our appreciation of its uniqueness. Either way, the search transforms us. When we look at Jupiter or Saturn through a telescope, we'll know that some of those dots conceal oceans, alien blue worlds under ancient ice. The cosmic ocean is not only above us in space, but beneath the ice of distant moons. As we explore, we carry the hope that in those hidden waters, we may find both an answer to "Are we alone?" and a deeper kinship with the universe, where the seeds of life like stars may be everywhere, shining in the dark. The story of life may not be limited to Earth. If you feel the pull of these hidden oceans and the mysteries they hold, subscribe to the Omega Signal to tune into the universe's deepest secrets. And if this voyage spoke to you, leave a comment, share it with others who wonder, and let's keep listening together for whispers in the cosmic dark.